Hello everyone, this side Manisha Mishra, Assistant Professor in Mathematics, Applied Science Department at St. Andrews Institute of Technology and Management, Gurgaon. And this college is affiliated to Maharishi Dayanand University, Rohtak. Today I will discuss few example of improper integral, and in our previous session I told you about evaluation of improper integral. So there are two or three examples here, and I will tell you about these examples, how we will solve these questions, and these questions have already asked in your final semester exams, right? So 2006 and 2009, but after 2006 and after 2009 it also be asked. So let's see, our first example is, so 1 minute. Yeah, okay. So this is our first example, and this example has been asked in 2006, and also I know that it also be repeated again and again. So evaluate minus infinity to infinity x square dx upon x square plus 1 x square plus 4. So this is our integral, and we have to solve this integral by our complex integral contour. That means we have to solve this question by the contour integration. So first we consider this function as integration c z square dz upon z square plus 1 z square plus 4. That means we will write this function as in terms of z. So we are writing here, right, and this is equal to integration c fz dz. Right now, where C is the contour consisting of the semicircle CR of radius R together with the part of the real axis minus R to R. So this language always be same in our each questions, where C is the contour consisting of the semicircle CR of radius R together with the part of real axis minus R to R. So this, guys, learn this three lines, and this lines always repeat in our each question. Now we have our FZ. So next we will find poles. So for the poles, you will put denominator is equal to 0. So denominator is equal to 0. So denominator is z square plus 1 into z square plus 4 is equal to 0. Z square plus 1 is equal to 0, z square plus 4 is equal to 0. So you will get z square is equal to minus 1, z square is equal to minus 4. So minus 1 value, that means iota square, and minus 4 you can write 4 iota square. Then taking roots, then you will get z is equal to plus minus iota, and here z is equal to plus minus 2 iota, right? Now z is equal to iota minus iota, 2 iota minus 2 iota. So first we need to check which one lie inside the circle. So check the integral has simple pole, right? These are the simple poles. Now you can see here z is equal to minus iota is a negative coordinate. That means z is equal to minus iota, you can write x plus iota, y is equal to minus iota. Then comparing on both sides, then you will get x is equal to 0 and y is equal to minus 1. That means 0 minus 1 will lie on fourth axis. That means in the lower half semicircle, lower half circle. Then this z is equal to minus iota does not lie inside the circle. That means we are considering upper half circle. So upper half circle does not lie, does not contain z is equal to minus iota. Same as it is, upper half circle does not contain z is equal to minus 2 iota, because these 2 points lies in the lower half circles. So that will not be lie inside the circle, and our circle is CR, right? So next we need to find residue of these 2 points. So which one is lying? Only z is equal to iota and z is equal to 2 iota will lie inside the semicircle C, right? Now find the residue at z is equal to iota. So limit z tends to iota, z minus I into f z, because these are simple poles. So simple pole formula here, and limit z tends to I, z minus I, z square, f z is z square upon z square plus 1, z square plus 4. Now you can write z square plus 1 as z plus I, z minus I. So limit z tends to I, z square upon z plus I, z plus 2I, z minus 2I, both will be cancelled out and you will have only this one. Now what you do, you will apply the limit here. So apply limit, so you will get I square upon I plus I plus 2I, I minus 2I. Then now solve this line and you will get 1 upon minus 6 iota. Then you can write it minus 1 upon 6 iota. Minus 1 value you know, I square. Then you can write I square upon 6 I. 1 I cancelled out, only I by 6. So you are getting the residue value at z is equal to I as I upon 6. Right? Now you have another pole, and pole is z is equal to 2I. So find the residue at z is equal to 2I. So you will get limit z tends to 2I, z minus 2I into fz. Z is equal to 2I, again a simple pole. So just z right here. So z square upon z square plus 1, z square plus 4, and z square plus 4 you will write z plus 2I, z minus 2I, right? So 2I square, 2I whole square upon 2I plus I, 2I minus I, 2I plus 2I. So 4I square upon 3I into I into 4I, then you will get 1 upon 3I. So you can multiply by I in the numerator and denominator, then you will get minus I upon 3. These are the residues. So you have two residues. So by the Cauchy integral theorem, or Cauchy residue theorem, what you have 2 pi I residue of fz at z is equal to I plus residue of fz at z is equal to 2I. So both of the residues, so you will add, so just simplify, then you will get minus pi square upon 3, I square value you can write minus 1, then your answer is pi upon 3. So integration C fz dz, you are getting pi upon 3 here. Now we need to calculate minus infinity to infinity value. So our integral will be, total value is, we are dividing the integral contour as CR and minus R to R for the real axis and for the semicircle. So this one is for the semicircle and this one for the real axis minus R to R. So minus R to R, that means total integral will be minus R to R fx dx plus integration for the semicircle fz dz, and you are getting whole value pi by 3, right? This is the equation first. Now hence by making r tends to infinity, then 1 will be, if you are taking r tends to infinity, then minus infinity to infinity fx dx plus limit z tends to infinity fz dz is equal to pi by 3. Now r tends to infinity, that means you are taking limit radius as infinity. If you are taking radius infinity, then this integral fz, this integral fz will be vanishing. That means it gives 0 for the infinity radius. For the infinity radius, that cannot be true. So this value, integral value, will be 0 when you put r is equal to infinity. So limit z tends to infinity, c r f z dz will be 0, and you will have only by the equation this one, you will have minus infinity to infinity fx dx is equal to pi by 3, and your fx value is x square dx upon x square plus 1 x square plus 4 is equal to pi by 3 is your final answer. That means you will take in each and every questions after solving after that term. That means by Cauchy-Residue theorem, and you will get your answer here. After that term, you will take always r tends to infinity, then your one part will be 0 at because radius is infinity, and that integral cannot be defined at infinity, so it will be vanishes, and it will be vanish, and the integral value will be 0. So you will write 0 here, and you will get your answer minus infinity to infinity fx dx. And what you are getting answer, so that will be your the value of the contour integral, right? Each and every question you have to follow the same process, nothing will be changed. But there are one or two questions here in which our residue method and few methods, no, residue, only residue method will be changed, that how we will find the residue at unity, roots of unity, right? So there is another question, and that question is also came in 2006. So guys, this question is very important, and I'm sure that it will also be repeat. So using complex variable, this is very important questions. Using complex variable, evaluate the real integral. So we need to solve this integral by using our contour integral, complex integral, right? So first, what is the first step of our method is let fz. So you will change your function in the terms of z. So fz is equal to 1 upon 1 plus z to the power 6. Now we consider integration c dz upon 1 plus z to the power 6. So this is our integral value, and these three lines are again repeating. C is the contour consisting of the semicircle CR of radius r together with the part of real axis from minus r to r. Right? Now if we have our object, so next we will find the poles. So for the poles, you will put denominator is equal to 0. So 1 plus z to the power 6 is equal to 0. Now you will have z to the power 6 is equal to minus 1. So I told you a question about roots of unity. That means z to the power 4 here, z to the power 6 is given, z to the power 6 is equal to 1. I think um, is given, was given, and I told you z is equal to 1 to the power 1 by 6. That is called roots of unity. Then 1 you will write cos 2 pi, because cos 2 pi gives positive value, and I sine 2 pi. So pi, 2 pi, 3 pi, sine always gives 0. So z to the power 6 is equal to minus 1 here. That means minus 1 value cos gives at pi, right? So z to the power 6, you will write cos pi plus I sin pi. Sin pi, 2 pi, 3 pi, 0 always gives 0. So doesn't matter what is the sign value. But cos pi always gives minus 1. Cos 2 pi positive, and cos pi negative. The even numbers always positive gives positive 1. Odd numbers always gives negative 1. Right? Now z to the power 6 is equal to, now this is your nth roots of unity. That means you will write it cos 2n pi plus I sin 2n plus pi. 2 pi means 360, so 2n pi and pi, so cos 2 pi and pi, so angle will be same, no change. So cos, you can write it cos 2n pi plus I sin 2n pi plus pi, right? Now, by the theorem of De Moivre theorem, you will write it cos pi plus I sin, cos theta plus I sin theta as e to the power I theta. So theta is 2n pi plus pi. So e to the power 2n plus 1 pi into I. Here De Moivre theorem is applicable. You can apply De Moivre theorem here. So you are getting z to the power 6 is equal to e to the power 2n plus 1 into pi I, right? Now z is equal to, so that power will be divide. So 2n plus 1 pi I upon 6. So this is we 6 roots of unity, right? Because power is 6 here. Now if power is 6, then your n will be, n is equal to 0, 1, 2, 3, 4, 5. So here just try to learn these steps there where it is coming from. -1, you will write cos pi plus I sin pi. After that, you will apply and for the nth root angle solution, so cos 2n pi plus I sin 2n plus pi, and you can write it by the De Moivre theorem e to the power I theta. So 2n plus 1 pi I upon 6 z. And again you can open the De Moivre theorem. So cos theta, theta is 2n plus 1 pi upon 6 plus I sin 2n pi plus pi upon 6. Right? Now we have our n is equal to 0, 1, 2, 3, 4, 5. So if n is equal to 0, right? First one, n is equal to 0. So n is equal to 0 means z is equal to, put n is equal to 0 here. So z is equal to e to the power 1, 2n plus 1, 0 plus 1 pi I upon 6. Then you will get z is equal to e to the power pi I upon 6. Then you can write it cos theta plus I sin theta by the De Moivre theorem. So cos pi by 6 plus I sin pi by 6, and pi by 6 value, so 180 upon 6, so 30. So cos 30 value is root 3 by 2. I sin 30, sin 30 value is 1 by 2. So you are getting root 3 by 2 plus I upon 2. Now, if n is equal to 1, so z is equal to, put n is equal to 1 here, so 3 pi I upon 6, 3 pi upon 6, you can write pi I upon 2. So cos pi by 2 plus I sin pi by 2, so 0 plus iota into 1, so iota will be here, right? If n is equal to 2, so 2 into 2, 4 plus 1, so 5 pi I upon 6, cos 5 pi upon 6 plus I sin 5 upon 6, and you can write 5 pi upon 6 as 5 pi plus pi minus pi by 6, right? 5 pi by 6, you can write pi minus pi by 6. So cos 180 minus theta minus cos theta, so pi by 6 value is root 3 by 2, so minus root 3 by 2. And here plus I sin 5 pi by 6, you can write 5 pi minus pi by 6. So sin 180 minus theta, again sin theta, so sin pi by 6 value is 1 upon 2. So minus root 3 by 2 plus I upon 2. Now, if n is equal to 3, so just n is equal to 3, 3 to the 6 plus 1, 7 pi I 6. So cos 7 pi upon 6 plus I sin 7 pi upon 6. So you can write 7 as pi plus pi by 6. Here pi plus pi by 6. So cos 180 plus theta minus cos theta. Sin 180 plus theta also minus sin theta. So cos pi by 6 value, sin pi by 6 value. Now, if n is equal to 4, so just write here n is equal to 4. So 4 to the 8 plus 1. Then that means 4 to the 8 and plus 1. So you will get 9 pi by 6. 9 pi by 6, you can write 3 by 2. So 3 pi by 2 I. So cos 3 pi by 2 plus I sin 3 pi by 2. Again, you can write pi plus pi by 2 plus I sin pi plus pi by 2. So cos 180 plus theta minus cos theta plus sin 180 plus theta minus sin theta. So just write the values here. Now again, n is equal to 5. So 2n plus 1, that means 5 into 2 plus 1. So 11 pi by 6. Now 11 pi by 6, you can write pi plus 5 pi by 6 plus pi plus 5 pi by 6. So minus cos 5 pi upon 6 minus I sin 5 pi upon 6. Now you know that value cos pi by 6 value. So you can write it from here. So cos 5 pi by 6 value is minus root 3 by 2. So minus root 3 by 2, and 5 sin 5 pi by 6 value is 1 upon 2. So you will get root 3 by 2 minus I upon 2. Now you have all your poles. Next you will check that which one is lying inside the circle. Okay. So let's check. So we can see here that which one are negative in y-axis. That means imaginary part. If imaginary part is negative, that means that pole does not lie inside the circle. Here check. So now n is equal to 0. imaginary part is positive, n is equal to 1, imaginary part is positive, n is equal to 2, imaginary part is positive, and n is equal to 3, this is negative, this is negative for n is equal to 4, n is equal to 5, this is also negative. That means negative imaginary part cannot be lie inside the circle which we have. We have upper half circle, so that cannot be lie inside the circle. That means only three poles will lie inside the circle, and that poles are e to the power I pi by 6, e to the power I pi by 2, and e to the power 5 pi upon 6, right? And here pi by 2, e to the power pi by for n is equal to, so the 1 by 2 point will be here, root 3 by 2 plus I upon 2 point will be here, and this will be here, right? So are inside the circle or in contour. Now, if these are lines at the contour, then we will find residue of these two. So guys, here there is a method to find the residue of the unities. So residue at z is equal to e to the power I pi by 6. We are taking first pole. So limit, these are simple poles. So limit z tends to e to the power I pi by 6. So what we are doing, in our previous questions for the simple pole method, z minus, we are writing z minus e to the power I pi by 6 into fz, है, right? And put the value of fz, then one will be cancelled out and other one will be remaining, and we just apply the limit, right? But here there are 6 roots of unity. If you will write e to the power, suppose z minus root 3 by 2 plus iota by 2 type say, so that will be your complicated, the calculation can be complicated. So we will apply that limit z tends to e to the power I pi by 6, 1 upon dz 1 plus z to the power 6. Simply d upon dz 1 plus z to the power 6. I told you this, you can check this method in our residue method, right? I told you this method. So 1 upon dz 1 plus z to the power 6. So the limit z tends to e to the power I pi by upon 6. So 1 differentiation 0, z to the power 6 differentiation is 6 z to the power 5. So just put the value of z here. So you will get 1 upon 6 e to the power to power multiplication 5 I pi upon 6. So final answer is 1 upon 6 into e to the power in the numerator. You will write minus I 5 pi by 6. Same as it is, residue at z is equal to e to the power 4 pi by 2. So limit z tends to e to the power pi by 2, 1 upon dz 1 plus z to the power 6. So again you will get 1 by 6 e to the power minus 5 I pi by 2, right? And residue at of fz at z is equal to e to the power 5 pi I upon 6. So limit z tends to 5 I pi by 6, 1 upon d upon dz 1 plus z to the power 6. So you will get e to the power minus 25 I pi upon 6, right? Now, by the Cauchy residue theorem, sum of the residue integration fz dz is equal to 2 pi I into sum of the residues. So first we are finding sum of the residues. So 1 upon 6 e to the power minus 5 I pi by 6 plus e to the power minus 5 I pi by 2 plus e to the power minus 25 I pi by 6. Now we can apply here De Moivre theorem, cos theta plus I sin theta is equal to e to the power I theta. So cos theta plus I sin theta all are applicable. Just write the value of these here. So cos 5 by 6 value is minus root 3 by 2. This value is this one. So just write all these value. We have already discussed in our above pages, and you will get your final answer minus iota upon 3. Right? So 2 pi I into sum of residue. So 2 pi I into minus iota upon 3. So 2 pi upon 3 minus iota square, and put value of iota square here, then you will get 2 pi by 3 is your final answer. So again you will write here that total integration of CR FZ plus minus R2R Fx dx is equal to 2 pi upon 3. Then you will take in R tends to infinity, then your CR Fz dz will be vanishing, and it will vanish and gives 0 value. Then you will take R tends to infinity, so minus infinity to infinity, Fx dx will be remaining. So Fx value is dx upon 1 plus x to the power 6 is equal to 2 pi by 3, and you need the integral value 0 to infinity. So this is an even function. You can divide the limit 2 times 0 to infinity, and your answer will be pi by 3. So this question is very important, so just try to learn this question by step by step. And this can be asked final semester exam, so prepare this question very carefully. Now there is another one question, and it is came in MDU December 2009. 0 to infinity dx upon a square plus x square whole square. So we will solve this question same as above questions. You are getting z is equal to plus minus ai as a poles, and which poles is lying inside the circle, only positive one. Then you will write it as well, just you will find the residue of this function, and this is a double pole, so you will apply residue at the double pole, that means pole of order n residue. So you will calculate and you will find your answer at these points. And if you guys any problem in this question, then I will repeat it again. Just try to understand this question, try to solve. And I have an exercise here, so just solve this exercise and tell me which one is you can solve, which one or not. So I will give you solution. And in our next session, in our next video lecture, I will start your second unit, ordinary differential equation, right? So in ordinary differential equation, I will discuss exact linear equation and the Bernoulli equation, like this. So I will start in our next session. And today is your fourth unit is completed. So guys, you prepare your third unit and fourth unit, and if you guys have any doubt, then ask me, right? Thank you.